Imagine for just a second that you are raising a pair of perfectly identical twins. Now, if one twin grows up in a completely different environment than the other, different food, different weather, different schools, they might start out identical, but over time, they aren't going to look or act exactly the same anymore. The environment actually changes them. Well, this exact same concept applies perfectly to microchip manufacturing. In analog layout, certain microscopic transistors are designed to be our identical twins. They absolutely must behave exactly the same way to function properly. But thanks to the harsh realities of chip manufacturing, tiny environmental variations inevitably pop up. So today, we are going to break down the totally ingenious layout matching techniques that engineers use to guarantee these microscopic twins behave equally, no matter what. Okay, let's quickly lay out our roadmap for today. We will start with the microchip mismatch problem. Then we'll explore 3 brilliant solutions: interdigitation, common Centroid, and dummy devices. And finally, we'll pull it all together in the ultimate group photo. All right, let's get into section 1, the microchip mismatch problem. So, in the high-stakes world of analog design, leaving your transistors to chance just is not an option. If 2 supposedly identical transistors aren't perfectly matched, the fallout across the whole circuit is pretty severe. Your operating currents will change unexpectedly, voltage levels will shift, amplifier performance will drop significantly, and those unwanted offsets will just keep increasing. Basically, it can completely ruin the precision of the entire chip. To really get this, let's ground it in something everyday. Suppose you step onto a weighing machine, let's call it machine A, and it shows 60 kilograms. Then you step onto machine B right next to it, and it shows 62 kilograms. Now, your weight obviously hasn't changed at all. The readings are different simply because the 2 machines themselves are not properly matched. When analog circuits try to read signals through unmatched transistors, they get these exact same frustrating, conflicting results. Which brings us to the critical engineering puzzle of our time. When you are dealing with elements smaller than a speck of dust, how on earth do you force microscopic transistors to experience their manufacturing environment identically? How do we actually make them behave equally? Fortunately for us, layout engineers have developed 3 brilliant frameworks to solve exactly this. Section 2, interdigitation, or mixing like fingers. Our natural instinct when placing 2 identical things is just to put them side by side, right? But in analog layout, that is exactly what we want to avoid. Instead, we use something called interdigitation. The definition of interdigitation is taking these devices and arranging them by alternating them, quite literally like interlocked fingers. The goal here is to reduce what we call local mismatch. So whenever you hear this term, I want you to immediately picture a pair of hands with interlocked fingers. It is the perfect visual anchor. Rather than grouping all of device A on the left and all of device B on the right, we alternate them. A, B, A, B. Think about planting an orchard of trees. If you plant one type of tree entirely on the west side of a hill and another entirely on the east side, one group gets blasted by the sun and wind, while the other just sits in the shade. The growth is going to be totally mismatched. Or imagine 2 cricket teams practicing on a field where only one side is getting heavy winds. The performance is going to be completely skewed. But if you interlock them, if you alternate every single tree or mix the cricket players evenly across the field, everyone shares the exact same wind, sun, and soil. By alternating transistors like fingers, every piece of the device experiences almost the exact same microscopic manufacturing conditions. Moving on to section 3, common Centroid, which is all about finding balance. Now, we are shifting from just mixing things up to focusing on perfect symmetry for those higher precision needs. Common Centroid is all about arranging devices symmetrically around a single central point to ensure they experience identical manufacturing variations like temperature gradients or physical stress. Think of a balance scale. Everything is shared perfectly around a central pivot. In fact, here is an easy memory trick for you. Common means shared, and centroid means center, so everything is perfectly balanced around the center. And honestly, I love this because it makes total sense when you think about everyday food. Think about a group of students standing outside. If they're clustered incorrectly, the ones on the left are freezing in the shade, while the ones on the right are sweating in the sun. That is a gradient error. But if we arrange them symmetrically, they share the environment perfectly. Or, to make it even simpler, imagine making a pizza or a sandwich. If you dump all the toppings onto just one half, the person eating the other half gets a terribly boring bite. But if you spread those toppings symmetrically and equally radiating from the center, every single bite tastes exactly the same. Common Centroid distributes our transistors just like those perfect pizza toppings. So the crucial point here is understanding exactly when to use which technique. Common centroid is arranged symmetrically around the center to remove gradient errors, making it heavily used in high-precision circuits. Interdigitation, on the other hand, alternates mixed devices, like interlocked fingers, to reduce local mismatch, making it fantastic for general good matching needs. All right, Section 4, Dummy Devices, the Bodyguards. You know, getting the core transistors arranged perfectly, that's actually not enough, because the edges of a microchip layout are a really dangerous place. Why do we need bodyguards? Because of edge effects. During integrated circuit manufacturing, the devices right at the boundary of your layout experience a very different reality than the ones sitting safely in the middle. At the edges, oxide thickness can vary slightly, chemical etching is often not uniform, physical stress levels are entirely different, and all of this leads to wild changes in current and threshold voltage. Simply put, the edges take an absolute beating. So to solve this, we bring in the dummy device. This is a completely non-functional transistor placed right at the layout edges. Its only purpose in life is to protect the actual functioning transistors from those harsh edge effects. I want you to picture a tough security guard. They don't participate in the circuit's operation at all. They just stand on the outside and take the hit from the manufacturing variations so the real devices inside remain completely unbothered and perfectly matched. If you love baking, this analogy is going to hit the nail on the head. Think of a freshly baked birthday cake, or maybe a pan of brownies. The center is always soft, moist, and perfectly baked, right? But the corners and the edges, they take the absolute brunt of the oven's heat. They get harder and slightly overcooked. If you want to serve the absolute perfect, uniform cake to your guests, what do? You cut off those hard edges and only serve the center. Dummy devices are those hard edges of the cake, or like the outer protective padding in a box of chocolates, or the empty seats at the ends of a drafty classroom bench. They absorb the damage so the core stays perfect. Finally, Section 5, the ultimate group photo. Let's actually put all three of these layout techniques together into one bulletproof strategy. Imagine you are organizing an incredibly important school group photo and everything has to look absolutely flawless. Step 1. You alternate the tall and short students so the heights are mixed evenly. That is your interdigitation. Step 2. You take that mixed group and arrange them perfectly symmetrically around the center focus point so the photo looks balanced and even. That is your common centroid. And finally, Step 3. You place the teachers at the far left and far right ends to protect the students from the edges and keep the whole group safely organized. Those are your dummy devices. I absolutely love this realization. Everyday logic, things like arranging a group photo, slicing a birthday cake, or even just interlocking your fingers, is the exact blueprint for mastering microscopic engineering. The rules that govern fairness and balance in our big macro world are exactly what engineers use to manipulate silicon at the atomic scale to ensure perfect harmony in analog layouts. It is an incredibly beautiful parallel. Well, thanks for watching. If you want more content like this, please do subscribe to my channel and like, share, and press bell icon. And hey, before you go, next time you look at your smartphone, I want you to ask yourself how many millions of microscopic bodyguards and perfectly balanced atomic groups are working tirelessly right now just to let you watch this explainer. Keep learning, and I'll see you in the next one.